Hello students, welcome to the video on combinational logic circuits, which is study unit 5. I think it's a short study unit, but it can be very confusing. So here we have the explanation of what combinational logic is, and when logic gates are connected together to produce a specified output for certain specified combinations of input variables and no storage is involved, the resulting circuit falls in the category of combinational logic. In combinational logic, the output level is at all times dependent on the combination of input levels. This study unit covers analysis of combinational logic. So, okay, what does that mean? So, we basically use logic gates to mimic other gates. And the output is always reliant on the input. So there's nothing stored, nothing happening. If one of the inputs change, then the output change. So specifically what we're doing is we're using NAND gates and NOR gates to make up other circuits. We use NAND gates to make NOT, AND, and OR, and the same with NOR gates for NOT, AND, and OR. Now we do this, so to simplify circuits, you have only one NAND gate IC, and you can implement your whole circuit through just that one IC instead of having different ICs for OR, AND, and NOT circuits. So here we use NAND gates to implement other logic functions. So first we use one NAND gate to act as an inverter. So we wire up the inputs like this in parallel. So one input becomes two because we wire the input to both of these, and it gets inverted. So if we wire a NAND gate like this, it becomes an inverter gate or NOT gate. Here we use a NAND gate, two NAND gates, as an AND gate. So first of all, A and B, and the result is this, A and B NOT. And if we further invert it using the gates like here we invert the output. So we have a double bar which then cancels out, and that's just A and B. So we can use two NAND gates to simulate one AND gate. Same here, we can use three NAND gates to simulate an OR gate. So what we do here is first we invert the inputs here by doing the double wiring, parallel wiring, and then we put it through an AND gate. So then our output is this bar and over NOT A, NOT B. So if we use De Morgan split the line, change the sign, so then it becomes double bars in A and B, which cancels out, and that's A or B. So three NAND gates wired like this is equal to one OR gate. And here we can use four NAND gates as an OR gate. Once again, we invert the inputs, we put it through a NAND gate, and then invert it again. And this is our output. So it's basically up to here. This line, this bit here, is the same as here, and then we invert it because an inverted OR gate is the same as a NOR gate. So these four NAND gates we can use as a NOR gate. Now we can use NOR gates to implement other logic functions. Here, well, the same as the NAND gate, we wire them together. It simply inverts the input. So same with the NAND gate, if you wire them one input to the gate, it inverts it. The same thing here, if we first NOR A and B together and then inverted, we can have a NOR gate uses an OR gate. So the same thing here, we have A or B, NOT, which is a NOR gate, and then we invert it, make another bar up top there, which cancel out until we have A or B. So these are the same. As well, we can have three NOR gates that work as an AND gate. So here we first invert A and B, and then we NOR them together, which is the output here, with A and B inverted and then NORed together. So once again, De Morgan split the line, change the sign, and then we have double bars on A and B, which cancel out, so it's just A and B. So this is the same. And then once again, up to this point is the same as this. So we use four NOR gates, for a single NAND gate. So we have this which is basically the OR operation, and then we just invert it like this. So these 4 gates can work as a NOR gate. So basically, a NOR gate and NAND gate you can use to implement all the basic functions, logic functions that we want. Okay. So now I have the example in study guide. I convert the following expression to a NAND gates only. So this is the expression we have. A and not B, or C not D. So first of all, we fling on, if there's a sign that we want to change, we fling on double bars. Because if you add a double bar, it basically cancels each other out, so you're not doing anything. So we fling on the double bar over this expression, which gives us this. And then using De Morgan to change the sign, we break the line, change the sign. So we have here the not, the inverted, the bar broken, and the sign changed to and this expression we can use to implement a NAND gate logic. And this is exactly what we did. So here you see we first invert the B and we invert the C, and then we feed them through NAND gates to get this, and then through another NAND gate, which gives us this output here. Now just follow each step. So invert B by wiring it in parallel like this, and then NAND it together with A. So you have A and not B, not. And here we have C, not C, so C wired parallel, not C, and then NAND together with D. So you have not C and D, not. And then we NAND these two together again. So that is that first part, that's the first part. And it's exactly the same as the equation we had before. Because with De Morgan, we can break this line and change the sign. So then these bars will cancel out, and you have A not B or C not D, which is exactly what we started from. So still unsure? Okay, let's do some examples, because it does take a while and you have to do a lot of practice and find things you can convert and see what the answers are. So here I've looked at section 3 in your textbook. Check up the section 3 checkup on page 257, and this is from edition 10. I'm only in future I'm working with the 10th edition, because that's the textbook I have. So it states using NAND gates to implement these expressions. So we must use a NAND gate to implement A not or B. So the rule is whenever we have a sign that we don't want, we fling up double bars, and then the first bar we use De Morgan. So we break the line, change the sign, and then this becomes this, which we can implement using NAND logic. So break the line, change the sign. So we have, and then we have a double bar on the A here, which then just becomes A, and then not B. And then this we can implement in NAND, as I said. So here we have just A, and we invert the B using the parallel wiring, and then we NAND them together, which gives us this. Now, once again, if we want to see if this is equal to that, we change the sign, break the line, change the sign. So we have A not or double bar B, which is just A not B, which is exactly the same. So this implements this. The second question, we have X equals A and not B. Now, luckily for this, we can implement as is. We don't need to fling up double bars because it's all AND logic. So first off, we can invert the B by using this parallel wiring, and then we can AND them together. But then to go from that spot to here, we can just we can invert it again by using parallel wiring. So then it adds a bar up there, and the two bars cancel out. So we have AND A and B not. So just going through it quickly again. We invert the B, we NAND them together, and then we invert this by using the parallel wiring. which then adds a bar up top there, but because there's 2 up top, it then cancels, and we have our answer. Now pretty much the same thing with NOR gates. Here we have an OR operator, which is fine, so we don't need to do logic simplification or change it. So first of all, we use the inverter gate. So this is a NOR gate, so we use parallel wiring to have the not A, and then we NOR it together. So not A or B, not. And then we invert it again, which I showed you have double bars, then it cancels out, so you have A, not, or B. So just going through it again, we invert the A, we NOR it together with B, so it's not A or B, not, and then we NOT it again through parallel wiring of the NOR gate, which then leaves us with our answer, which we want. So here we have, we must convert, or we must use NOR logic for A and B not. So here we have to change the sign. So we fling up double bars, using the mortgage, break the line, change the sign. So now we have not A or double bar B. So we have not A or B, not. So then to implement this with NOR gates is easy. So A not, we invert it using the parallel wiring of a NOR gate, and then we NOR them together. So you have so we invert A to have A not, and then NOR together with B. So you have A not or B not, which is the NOR operation which we want. So once again, check if you're right. Using the Morgan, break the line, change signs, break a line, change the sign to an AND. There's a double bar on the A, so it's A and B not, which is the answer we want. So just to remind, if we are using NAND gates, we try to eliminate all the OR operations by adding a double bar. Same thing if we want to use NOR gates, we use a double bar to eliminate the AND operators. Okay, so still a little bit unsure. Let's have a look at section 4 checkup on page 262. So here it says implement expression using NAND logic. So this is the expression we have. So first of all, we use NAND, so we know that we don't want any OR operators. So, but here we are fine, so we leave that alone as is because we can implement the AND operations pretty easily. So here we have what we need to change. So we fling up double bars atop this brackets, just these brackets, like this, because we can, because it's like it's ANDing with A1, which doesn't do anything. No, well, they cancel out. So we do it like here. We use De Morgan, break the line, change the signs, like so. As you can see, all of them have double bars, which cancel out. So then we have A, B, C not, and D and E not, which we can use NAND gates for. And here we need NOR logic. So as we can see as well, okay, so NOR, so we're working with OR gates, so we don't want the AND logic. So here we put a double bar on top of the A not A and B not and C not. So we put it up there, and then once again De Morgan, break the line, change the sign, like so. So you have double bars here, and you're left with this expression, which we can implement using a NOR gate. So basically I have one NOR gate feeding in A, B, or C, and then another NOR gate feeding that answer and D and E. Okay, so it's pretty simple if you keep your head about it. Just remember the rules that we're working with, and remember if you're using NAND gates, you do not want any OR operators, and if you're using NOR gates, you don't want any AND operators. Remember the double bar and only change what you need to change, and do lots of exercises and so you get comfortable with this logic. Good luck.